Yes.
Okay, so, oh look, it's Travis. Where's Travis? Travis, tell us what we're going to talk about today.
Something about interactions and symmetries.
Sweet, good. That was a really nice summary. Tell me the more interesting part of the pre-lecture reading.
Hold on, I got it right here. I read it like 4 times, and I was like, I still don't really understand this.
That's okay. You don't have to understand it. It's just to get your brain, to get the gears turning.
We'll cover the simplest case of an
No.
internal.
The very first part.
Oh, this class is as good as DR?
Yeah. We're gonna fix that.
That was not just me.
Yeah. Okay. I hear you. All right. Okay. So we have a pretty tight schedule to keep to for the 3 remaining lectures leading up to spring break, and I want to try and make sure I get through the topics so that there's kind of a nice natural break. So what we're going to do today is we're going to introduce interactions, and in case you haven't been paying attention, so far everything we've talked about in terms of Lagrangians and equations of motion have been for free fields, that is, fields that have no interaction. So literally in sort of mundane particle speak, this is just a particle which is flying through space doing nothing else. Okay? And we've uncovered a lot of technical information, which doesn't seem as sexy to some of you as it could be. But we unearthed these 3 Lagrangians, which we're going to see at various levels in the standard model. For spin 0 particles, we have the Lagrangian, which gives rise to the Klein-Gordon equation. For spin 1/2 particles, this Lagrangian gives rise to the Dirac equation. And then for spin 1 particles, this Procke-Lagrangian gives rise to the Procke equation, where in each of these, phi is the scalar field, psi is the spinor field, and A nu is the vector field, or the spin 1 field. Okay? Now, in the standard model, each of these kinds of fields are going to play different roles, all right? The spinor fields are going to be sort of the most crucial. They're sort of our starting point because all matter, all stuff, are fermions. They're spinors. They're described by spinor fields. So this is going to be the Lagrangian that we start with, all right, when we just have the stuff that's out there. These we're going to find come into play when we talk about forces, and then this is going to come into play when we talk about Higgs mechanism. All right, so our starting point today is going to be, let's suppose we have some stuff, and then we want to get that stuff to interact and have some interesting interactions. So we want to add dynamics to our story. Okay, so you might ask yourself, and I should supplement this one with the definition of FU nu. And I'm going to keep writing this, and you might say, Foreman, why do you keep writing that? We know what it is. Well, one day in the near future it'll change. So I want to keep reminding you what it looks like up to the point when it changes. And we'll understand why then. So these are what free Lagrangians look like. In a sense, they're similar. We've talked about why they have their differences, in particular why the spinor Lagrangian looks a little bit different, having only 1 derivative instead of 2. But nonetheless, they all share common features. For example, these first terms in each of them are the derivative terms. And in some level, they're a quadratic derivative term, although again, the spinor term is a little bit of an oddball. Okay, if you were going to interpret these quadratic derivative terms, what would you relate those to in terms of normal sort of motion of particles?
I guess like acceleration.
Close. It's first derivative.
Oh.
So when I say quadratic, I mean a square of the derivative, not the second derivative. So what would you relate that to?
I just need velocity, energy.
Yeah, it's like having velocity. So you can think of these as the velocities of the fields, but we know in relativity that the kinetic energy per se has an additional contribution, and Patrick will be happy to tell us what that additional contribution is in relativity. So you have the velocity of motion, but you also have you have the energy of motion, but you always also have the energy of. Well, that's true in anything.
Right.
But what's the new form of energy that special relativity brings into the game? You want to phone a friend?
Yeah.
Maybe I'm not asking the question in the clearest way. Matt?
Rest mass?
Yeah, rest mass energy. And that, of course, is captured in the second term in each of these. So what we're seeing in these free Lagrangians is basically the kinds of energies you could have as a particle with no interactions. That is, you can be moving, so you have some kinetic energy of like associated with velocity, but of course, just existing, you have to have rest mass energy, and that's captured by this outcome. So you might ask, okay, well, what would an interaction term in a Lagrangian look like? If I had two fields which were interacting, what might we expect the interaction term to look like? And the answer is simple: no. No. An interaction term between, say, a spinor and a scalar field would just be some number, something, times a product of those fields. Okay? Literally, it's that simple. If you have two fields that are multiplied together in some term in the Lagrangian, then there's an interaction between them. The value at a certain point of this impacts the value of that. Okay? Now, you're not limited to just a quadratic. I mean, you could have, all manner of powers and contributions. And you could even have a derivative of a field. Okay? What makes it an interaction is essentially that you're multiplying different things together. These, if you will, are all self-interaction terms. We would probably leave off the word interaction there, but they're sort of self-relational terms. This is phi squared, this is Sidebar psi, this is Sidebar d mu psi, okay? So interactions are going to be essentially encoded in products of fields and derivatives of products of different fields and derivatives of different fields. You can have any higher power that you want, and the only restriction we have so far is that whatever these interaction terms might be, they would need to be Lorentz invariant, because after all, we're doing special relativity. We should need to make sure that our Lagrangian is overall a scalar under Lorentz transformations. Now, Hayden,
Yes.
does that really limit us very much? How many terms could you write down, could you cook up that would be Lorentz invariant, allowing yourself all possible products of fields and their derivatives? How many do you think you could do?
Probably a lot.
How many is a lot? Give me a number. 4 is close. Anybody want to help them out? No. You've taken this course before. You're a ringer. No. Anybody want to help them out besides Matt? Yeah. Yeah, there's an infinite number of terms. You were pretty close. Or infinity, yeah, if you can do as many powers as you want, you can obviously take this to infinity. So right now, without any further restrictions, it seems like there's no end to what we can do with interactions. All we have to do is make sure they're Lorentz invariant. Okay? Now that is not interesting. Like there's no sort of structure telling us what is really going on. And what we're going to find in the course of today's lecture and develop in more detail over the next 2 lectures is actually there is a rule that tells us what the interaction term should look like. And it's a very elegant, very simple rule. But that being said, this rule gives us the interactions which describe everything we've seen in experiment to date. Towards the end of the semester, we're going to actually unearth a very deep truth that points towards physics beyond what we've seen in accelerators. And in order to describe that physics, we actually do have to introduce all infinite terms. But more on that later. Right now, as far as the standard model goes, and just reproducing what we see in accelerators, the following rule, this following set of ideas for generating interactions will give us all of the interaction terms that we need, and it turns out not to be that many. Certainly not infinity. Maybe more than 4, but okay? But just bear in mind, when looking for interactions, this is the kind of thing you're looking for, just products of different fields. As soon as you see it, you say, ooh, it's an interaction. All right, so there is a sort of a recipe that we're going to follow, and we're going to follow it, and it turns out that this recipe is going to not only account for the electromagnetic interaction, but it's also going to, with a tiny modification because they're more technically sophisticated, it'll also account for the strong interactions and the weak interactions. But moreover, it also accounts for gravitation. And so hopefully if I can, towards the end of the lecture, I'll make some connection to that. But I'm not going to write this out in words because it's going to be borne out through the example that we do, but I'll read it out and then you can actually see it in the lecture notes online. But the program is essentially, we start with a free spinor field. We start with matter that's not interacting, and we either notice a symmetry of that, a global symmetry of that, or we modify it ever so slightly to have a global symmetry. So today we're just going to notice a global symmetry. The next time we're going to slightly modify this to give it a different global symmetry. And then what we do is we take that global symmetry and we make it a local symmetry. Now right now these words global and local don't mean anything, and I'm going to define what they mean in the course of today's lecture, do an example. But in making the symmetry local, we'll discover that we have to introduce interactions. So the interactions of the standard model, and in fact general relativity as well, follow from imposing a symmetry. I don't know about you, but I like that. I think that's pretty cool. And then the last step is, once we've introduced the interactions, the new interaction field can't propagate until we give it a kinetic term of its own. And so once we provide the kinetic term for the the new interaction field, or the mediator field, then we'll have a complete Lagrangian to describe our interactions. Okay? Yeah, Matt.
So are the symmetries that we impose related to what we observe in the experiment?
Of course. I mean,
So
yeah.
is that the idea? You take something you think should be true and you impose it?
Well, so I'm not interested in teaching this class from a historical perspective because that's hard. So the truth is nobody sat down and worked all of this out from the get-go and got all the answers and then went and did the experiments and verified it all. There was a lot of input from experiment. For example, QCD, there had to be experimental results that sort of pointed towards 3 different colors of quarks. Okay? We're not going to review that experimental evidence and the subsequent confusion and the missteps towards theories that didn't work. We're just going to go straight towards, there are 3 colors of quarks, let's write down a theory based on that. Okay? But yeah, everything is motivated by experiment. However, the example that I'm going to talk about today was actually at some level preceded experiment. Its original formulation was way back in the early part of the 20th century by Weil. And he wasn't actually trying to do quite what we're going to do, but he stumbled upon the same set of steps. All right? So yeah, everything is motivated by experiment, but I don't like to teach this from a historical perspective because the historical perspective is got a lot of unnecessary complications, which in the final picture of it all, it's a lot clearer than trying to look at it through this sort of twisted view of the historical evolution. You can certainly read Griffiths. He has a nice account of all the historical inputs from experiment. Okay, so here we go. We're going to start with the Dirac-Lagrangian, which I think I might actually finally have right with the correct signs. All right, and what I want to do is I want to, and remember that the adjoint spinor is defined as I gamma naught psi, complex conjugate transpose, so I gamma naught psi dagger. And what I want to do is notice that this thing has asymmetry. Recall, psi is complex. It's a complex spinor. So we could imagine transforming psi by the multiplication with some phase, iq phi psi. Okay? Now, q and phi are constants. And you might say, well, Flournoy, you know what E is. You know what I is, but why do you put in 2 constants? Why not just 1 constant? Well, in a few minutes, we're going to make these things play very different roles. So right now, it's good to give them 2 different labels, even though they're both just constants. Okay? At some level, this is just truly a constant, and this you can think of as the parameter describing how much you want to transform by. So the thing that you would vary to get different amounts of transformation would be this phi. But again, it's going to play an even more different role in just a few minutes. But if I consider this transformation, then psi bar would transform to psi prime bar. And if you just think about it for a moment, okay, remembering this definition of psi bar, the I gamma naught doesn't care what you're doing. So really and truthfully, when you transform this thing, you're transforming it, and then you're taking the Hermitian conjugate of the transformation. So this guy actually just becomes psi bar e to the minus I q phi. And then taking all that together, we find that the Lagrangian gets transformed into this new form. I literally just plugged in the new psi and psi, the new transform psi, the new transform psi bar everywhere they appear here. And we notice something nice, right? What do you notice? What happens? Yeah, so let's start over here on the right. Here I've got the transformation times its inverse. That becomes the identity. Okay. Here, if I could drag this guy over here, then those would combine to give me the identity. Can I do that?
Yes.
Sure. No reason why I can't. Okay. So those will combine to give me the identity, and lo and behold, you notice that we get back the Lagrangian we started with. Okay. Everybody see that? Now, I didn't have to actually do anything to the Lagrangian to get it to have this symmetry. It already has the symmetry by virtue of the fact that psi is complex. And in fact, any complex field that we write down, even if we wrote down a complex scalar field, it would also exhibit this symmetry. Okay? Next time, our starting point is going to be working with a different symmetry. So we're not going to be able to just start with this Lagrangian by itself. We're going to give it a little bit more structure. It's going to look the same. It's just going to have an extra little index floating around that we will show for a little while, and then we'll throw it away. No, it's a color index, actually. But anyway, so we've got this nice symmetry, and this is what I would call a global symmetry. So L is invariant under global transformations. Of the form e to the iq phi. Now global, what do you think the word global means? Marcus? What do you think I mean by the word global?
Not local.
Witty, but give me more than that. You can tell me what local means if you want to define it by its opposite.
So local is like the transform like some differential like r or just at a point, while global is like over the I guess the whole space.
So yeah, that's definitely in the right direction. So global means that we're doing the transformation, but we're doing the same transformation at every point in space-time. By contrast, we could also consider a local transformation. A local transformation would be a transformation where we're doing a different amount of the transfer. We're doing the same form of transformation, but we're doing a different amount at different points in space. We're doing it differently at different points in space-time. So to write down the form of a local transformation is actually straightforward. We just give phi, the transformation parameter, dependence on space-time. Okay. So now we see why it was kind of actually important to keep these two things separate. Q is legitimately just going to be a constant. Okay? But phi we're going to promote to something which depends on space-time position. Okay? This is going to be a local transformation. And you might guess that there is no way in hell that this is going to be invariant under the local transformation. And of course, we immediately see the problem, right? Travis. are you? Traber. What's the problem? If I want to make phi local, so instead of rewriting all this, I'll just do that. So everywhere you see phi now, phi depends on x. What can't we do that we did before?
Derivative?
Well, you can't take the derivative. You can take the derivative, but you...
It's not constant?
It's not constant, therefore we can't do what that we did before. Everybody, I think you can phone a friend because you got like 6 people that are dying to tell you. What can't you do?
You can't let it commute with the derivative.
Yeah, you can't just take this guy and now pull him across the derivative. No, no. Exclamation point, exclamation point. Okay? This is a basic fact from calculus. Constants you can always move back and forth across derivatives because they're constant. But the minute something has a functional dependence on whatever you're taking the derivative with respect to, you can't just arbitrarily move it. You can take the derivative, and we will. You just can't move the thing across. Mark.
So we
Okay.
we can like notice that there's this global symmetry, but we're going to try and impose a local symmetry. Is there an argument for trying to impose the local symmetry?
Yes, because when we do, we get a theory, and it describes everything we see in experiment.
But so it's an experiment.
A priori, no, there's no reason to think that this should yield anything. But magically, it yields every interaction that we've known, that we've seen. Every fundamental interaction is generated this way. Okay, so, I mean, to me, that's sort of a posteriori motivation.
Well, yeah, that makes sense.
Okay, yes? Mark?
So if we were, I'm not sure what you mean that, but if we were to expand the d mu e to the size of product,
We're going to. We are literally about to do that.
because then we would swap them.
Yeah, because right now, this is not invariant. By the way, so no. Now, I got to be careful because I wrote it all out in my notes, but I'm going to try and be efficient on the board. So let me know if I don't seem to be filling in a change. So remember now, all the phi's that you see depend on space-time position. I'm going to suppress that because it'll get cumbersome. Okay, so we would like to fix this. So to fix it, let's actually figure out what this thing looks like. Well, actually, no. Let's do it this way. I'm actually going to repeat this, but now I'm going to go ahead and propose the fix. All right, so So what I'm going to do now is I'm going to take my Lagrangian So this is a new Lagrangian. This is not the old Lagrangian. I am changing the Lagrangian, okay? It's going to look a lot like my old Lagrangian, with one exception. The derivative is going to be different. Where the derivative now is going to be d mu minus, let's see, plus I q a mu. Okay, so it looks like a weird derivative. All right? I is I, not me. Q is the same Q that we've been seeing. And this, right now, is just some dual vector field. Okay, this has space-time dependence. It's not a constant. So, for example, we should be thinking of taking derivatives of it. Now, I'm going to work with this Lagrangian with this new derivative, and what we'll find is that this Lagrangian is invariant under the local transformation as long as A transforms in a specific way, which we will determine in just a moment. Okay? So let's see how this works, okay? So, So let me write it out long once. it's plus. The glare from the lights off this board makes it very hard. Damn it. I can't see what's over. I can't see what's right there. Might as well not be there. I, Q, H bar, C, sidebar, gamma mu, A mu, psi, plus MC squared, sidebar, psi. Okay. Now when we transform this, again, we just replace everything by its transformed version. So we already know how sidebar transforms. And again, my phi has space-time position dependence. I'm not gonna explicitly write it. So this should look a lot like what we just did in the previous step. The only new thing is this second part of the derivative, which I've actually pulled out. Alex?
So I understand why you've changed the Lagrangian this way in order for it to be invariant, but how does that describe the same system if you arbitrarily change the Lagrangian?
It doesn't.
Okay.
It doesn't. It's a different system.
Okay.
But what we're going to find is that the different system. Well, I don't want to ruin my punchline. Okay. So we are changing the Lagrangian. I agree, but that's okay because the physics that we started with was pretty boring. It was a free particle. We want something else. So changing the Lagrangian is okay.
Okay.
But the point of this is that we're not just willy-nilly making some arbitrary change to the Lagrangian. We are changing the Lagrangian in a very specific way based on this symmetry principle. And it might not look all that cool in this example, but when we look at the strong interactions, okay, it's amazing that it actually gives you the structure of the strong interactions because they're much more complicated, but the same basic procedure gives you the right answer. Jacob? No? Okay, good. All right, so we already noticed a couple of things. This is, as usual, invariant because they just multiply together as inverses. Notice here that I can take this guy and drag him over there because there's no derivative separating them. Okay, so those will combine to give me the identity, but you have to be careful because I still have the new A in there. And I haven't told you what that is yet, but that's okay. All right. Now, in order to complete the story, we actually have to take the derivative here using the product rule. Okay, so if we do that, now I'm going to do this in words and then write the results, so pay attention. If I first take the derivative of, I'm going to go ahead and take the derivative of psi first. Okay, so this will come out, and when it does, it will cancel that. So that's just going to leave me with psi bar gamma mu d mu psi. Okay, that's letting the derivative act on the second term first in the product rule. But now I got to go back and let the derivative act on the transformation. This is just the derivative of an exponential, so I get the coefficient times the derivative of the thing that actually depends on position. So when I write that down, I'm going to get an IQ I'm going to get this transformation, but after I take the derivative of this, I'm still going to be left with that exponential. And then it can cancel this guy. So the taking of this derivative is really just pulling down the exponent with the derivative of phi. Okay, so that's what that term looks like. Everybody on board with that? I put in all the steps in the notes, but I'm just trying to be economical with time. And then we still have this term. And then the mass term, as we've already pointed out, is invariant. Okay? And now, we can make an observation. If A mu prime is equal to A mu minus d mu phi, what happens? Yeah, if A mu prime, if the new version of A mu is the original minus the derivative of phi, plugging that in here is going to give you back this term with A mu itself, and then the minus d mu phi is going to make this term exactly opposite this term, canceling it off. So in the end, this is locally invariant. Okay. Everybody see that? Everybody on board? Everybody good? 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 Yes?
I just have a question about why we're able to pull the E when we have the A mu prime inside of it, because if we don't know how that transforms, is there not a possibility that we would not be able to pull the E?
This is a field, it's not an operator, so
okay,
it
so
it doesn't contain any derivative acting on things. I mean, A mu prime involves a derivative, but this derivative doesn't act on anything further to the right. Yeah.
Isn't this just a gauge transformation?
You are insightful. He said, "Isn't this just a gauge transformation?" Well, let me come back to that in just a second. But let me, if you haven't already noticed, point out the very interesting part of our new Lagrangian. Does anyone see it? It has an interaction. It looks complicated, but what is it? It's a product of size and A. This is an interaction. To get this theory to be locally invariant, we have to introduce interactions. Thinking about it backwards, interactions are a way of letting things be locally invariant. They're sort of compensating for the fact that you're trying to do things differently at different points in space-time. Okay? So I'm going to come back and give this an interpretation, and I'll bring back this gauge transformation idea in just a second. But there's a third step to this procedure. So we had our original Lagrangian. We noticed a global symmetry, and then we asked, well, can we promote that to a local symmetry? To do so, we had to introduce a new field, and we found that that field has interactions with the original field we started out with. Okay? But now, at this stage, A mu is not that interesting because, for example, you would not take this Lagrangian and vary it with respect to A mu. You wouldn't get anything meaningful out of that. Okay, because there's no derivative of A mu. A mu is a background at this point. It's something you could specify, but you can't really get equations of motion that determine its form. So to get meaningful equations of motion, we have to let A mu itself propagate. We have to give A mu a kinetic term. Now, if I were in the business of figuring out what kinetic term might I give to A mu, what do you think I might look to? The Proca-Lagrangian. Okay. So perhaps we can try to give A mu a kinetic term from the Proca-Lagrangian, and let's see if that will work out. So I'll see if I can squeeze this into this space over here. So the Proca-Lagrangian is 1/16 pi, and I'm going to write this out. It's d mu A mu minus d mu A mu eta mu lambda eta mu rho d lambda A rho minus d rho a lambda plus whatever 8 pi. You guys, are you at all getting the sense of why particle physicists set C and H bar equal to 1? Yeah. Anyway, okay. A mu, or A nu, it doesn't matter what you call it, it's repeated. Okay. So this would play a nice, yes.
Are those the A in our d mu and the A in our f mu, are those the same A's or are they just different fields?
Are they, so is the A here the same as the A here? Yes. So what I want to do is I have this Lagrangian that has this field A in it, and I want to give A a kinetic energy term. If I'm going to use this, it needs to be the same A that's in there.
Okay.
Okay. But we have to ask an important question about adding in this kinetic term for A, and that is, am I going to undo what I did? Is that thing gauge invariant? Is it invariant under this local transformation? Okay, so let's investigate that. And oh my God, that looks terrible. Yeah, we can do this. All right. So I'm going to plug in the new A everywhere it appears. And remember the new A, where'd it go? There it is. Okay. The new A is A mu minus d mu phi. Okay. So when I do that, and I'm just going to rush through this, I'm going to get something that looks like this. This is algebra. You guys can plug this thing in. It's not hard. Okay. So after I plug in the new form of A after this local transformation, that's what the Procol-Lagrangian turns into. And the question is that what we started with? Is it invariant?
Yes.
Okay. And if we poke around in here, we start noticing, well, this is d mu, but they're partial derivatives. So you can always flip them. So those cancel. Same thing happens down here. Well, damn Skippy. D mu A nu minus D nu A nu. Factors of the inverse metric, D lambda A rho minus D rho A lambda. That's what I started with. Okay? But this presents a problem. Is this invariant? No. And there's no amount of multiplying out and manipulating this is going to make it go back to that. It ain't going to happen. Yes?
You just set the mass equal to 0?
That's what we have to do. So what we've just discovered is that the mass term in the Procol-Lagrangian is not gauge invariant. So if we want to use the Procol kinetic term for the gauge field, for this new A mu field, it has to be massless. Okay. So in the end, we can write down what our final theory looks like. And I should be a little bit careful. I'm not even following the rules that I tell Physics 1 students to follow. This m would be the mass of the gate of the A mu, whereas the m in the Dirac equation here will be the mass of psi. I'm just not going to label all the masses with subscripts. Hopefully the context will tell you what it is. But now it doesn't matter because I'm setting this to 0. It doesn't mean I have to set this to 0. This term was fine. Remember, that's the one that always worked out. It's this math term that gets screwed up. Yes?
I feel like you should be labeling your system.
Anyway,
Where's our FPD?
you guys go to hell.
So is there,
Okay. So at the end of the day,
We're saying that one of our fields, the spinor field, is mass, like has mass for our interaction with the AU field. That field needs to be massless.
are you talking to me? I thought you were talking to someone else. Yeah, sorry. Say
So the field, our spinor field is massful, whereas our AU field is massless.
Yes, yes. You could take the spinor field to be massless if you like, but you do not have to. You have to take the AU field to be massless. That's the point. Yes.
So does that tell us that the force carriers would have to be massless?
So let me get the final form of this down, and then we'll start talking about interpreting it, and that is going to be a very, very interesting question to ask. Okay. So our final Lagrangian, with all terms included, is going to take the following form. Okay, where this is invariant under local e to the iq phi transformations. Well, I'm multiplying by a complex exponential. It probably doesn't take too much work for you to realize that if I call this thing u, and then I multiply it by its Hermitian conjugate, that's the identity. But this is a number, so if you will, it's a 1-by-1 matrix. We've encountered this before. What do we call it? This is a transformation. It would form a group. What group does this correspond to? So it's unitary, and it's a 1-by-1 matrix. It's U1. Okay?
But is SU1 the same as U1?
So there's no need to distinguish S in the U1 case.
Okay.
well, how does it do with consistently changing the positive name?
So the S is useful for decomposing UN down to SUN cross something, but you don't decompose U1 to a subgroup. There is no non-trivial subgroup U1. Okay. All right. This we might as well give a name. It's electromagnetism. And now every word that you've ever heard applied to electromagnetism we can extract from this story. For example, what is this? It's the electric charge. Hence the name. Why do I say that's the electric charge? Well, think about it. This is an interaction between a field and the electromagnetic field. The coefficient generally determines the strength of that interaction. Well, what physical thing determines how strongly something interacts with the electromagnetic field? The charge. For example, if the charge is 0, it doesn't interact. Okay? I know that there's factors of I, H, bar, and C in there, and they have to be there, but they're not necessarily tied to the transformation like Q was. Q was part of our defining transformation. Yeah.
This is also invariant under global transformation, right?
Under global? Yeah. So that's an interesting observation. Anytime you have a local symmetry, it's automatically a global symmetry because you could just set this to constant. The converse is certainly not true. If something's invariant under global transformations, it's not necessarily invariant under local. In fact, that's what we just did to fix it. Okay, yes?
So is our mass, when we were discussing the mass, is the mass of the field, are we going to extrapolate that to a mass of like the electron then, for the field we're working with?
Okay, so far I haven't identified what kind of matter particle psi corresponds to. And now we can ask the question, if I actually wanted to do specific particles, what would I do? And then it just depends on what you want to work with. So if you want to describe electrons, you would use the electric charge of the electron and the mass of the electron in the formula. Okay? If you wanted to describe quarks, they carry electric charge. Okay? You would put in the electric charge of a quark, which turns out to be a fraction of an electron charge, plus or minus 1/3 or 2/3, and then the mass of the quark in question. You could do it with neutrinos, but the result is boring because neutrinos do not have charge, so this term drops out, and the neutrinos, at least as far as what we're going to talk about in this course, are massless. And so you wouldn't get these terms. So the neutrinos would not be very interesting. They decouple from electromagnetism. Okay? This guy right here is what we often call the electromagnetic field strength. Right? And that is certainly something you will encounter in advanced D&M at some point. Okay? This is the thing that actually you can write down as a matrix of electric and magnetic field components. A, and this is an unfortunate, this is a misfortune of my notational choices, but the for dual vector A is comprised of exactly the, do you have another symbol for electric potential other than phi? What do you guys use? Phi? V, oh, V, okay. And then the vector potential. Okay, so from electromagnetism, you're used to these ideas of the scalar potential, which you can take the gradient of to find the electric field, and then the magnetic vector potential A that you can take the curl of to find the magnetic field. Okay? These are the things that you actually combine, these potentials are the things you combine to create this four-component A mu. So this is the electromagnetic potential. So this is interesting because in this whole context, it's actually the potential that you introduce directly. The electric and magnetic fields themselves come at this step when you introduce the field strength tensor to give this thing a kinetic term. Okay? But the fundamental thing you have to add to get the symmetry is A itself. Now, from electromagnetism, your courses in electromagnetism, you are well aware that this enjoys gauge invariance. You can transform this thing, and it doesn't change the content of electromagnetism, and the transformations that you're allowed to do are exactly gone. Are exactly these. Okay? It's a goddamn shame when you learn electromagnetism that they go, oh, and you got this funny little thing that you can do? Yippee. You know, it's so understated in electromagnetism that the importance of these gauge transformations. And I will honestly tell you, most card-carrying physicists do not appreciate the fact that it is the gauge transformations of electromagnetism which are responsible for electromagnetism. And in fact, it is a perfect analogy of this that is responsible for all of the forces in nature. So treating this as an afterthought is a shame. Okay? For us, it is the critical component of electromagnetism, this idea of gauge symmetry. All right? And by the way, all of what I'm talking about now, we can just go ahead and convert this to the language of these are gauge transformations. The word gauge has meant different things in the historical context, but we can now think of it as, once I've made the transformation local, I would call it a gauge transformation. Yes?
So are phi in that transformation from A mu to A mu prime, is that the same as the V in...
No. That's why I said it was bad notation.
Okay.
So
what's?
So this is just a scalar.
It's just,
Okay, it's a scalar. It's not a field. It's just a scalar function of position that determines the transformation parameter. How much am I transforming at each point? Okay. That's why I didn't want to put phi there. Yes, Peter.
And for these gauge transformations to hold true, you still have to assume that A mu is massless.
Okay. So let's go ahead and make the connection to electromagnetism first, which is, in electromagnetism, what we have just discovered from this construction is that this thing is massless, but of course, in terms of particles, what particle would this correspond to? The photon, which we know to be massless. So in answer to Martin's question, if this is broadly applicable to more complicated symmetries, which we're going to investigate in the next 2 lectures, we're always going to reach this conclusion that in order to have invariance, the mass term has to be 0. And that is going to present a significant problem when we go and compare with experiment. Because experimentally we know that at least for one of the forces, the force carriers are massive, very massive. And solving that problem is going to bring us to the Higgs mechanism. Okay. Yes?
I have 2 questions. Is this Lagrangian to the TNM somehow like related to the one for the strong force? Because like
Is it related to the one for the strong force?
Right.
Yes. Yeah. I mean, it looks, the strong force Lagrangian is going to look very similar, but there's going to be some extra hidden structure because you're going to have sort of, it's going to be not one thing psi, but 3. They're going to form like a little 3-component vector. But that's the point, that's Thursday's lecture. So let me not jump ahead to that. You're going to see the strong force. You're going to see exactly how it's related to this, but what's different. But I don't want to go over that now because that's the point of Thursday's lecture.
And my second question is,
You only get one question.
that E and M and not E and M, yeah, E and M and the weak force are somehow related to each other.
So that is going to be the point of next Tuesday's lecture. It's talking about how electricity and the weak force are unified in what's called the electroweak theory. And I have to say that's going to be the most painful part of the course. But anyway. And by the way, I've already had to recalibrate our goals, so we're not getting to Higgs till the day after spring break. So don't think we're going to get to Higgs before spring break. Yes, Martin?
So is Q here just going to give us the coupling strength of the particle to that force? Or is there something else that we
So the way that you should think about it is that this Q tells us the coupling between these fields. But that's an interaction. You're going to have to get out of your head this word force. I know it's the way that you've been brought up to think about it in terms, from the earliest physics 1, whatever. Okay? But the truth is that the way you think of force when you start talking about the other interactions is just not as clear. You certainly can't draw like field vectors and say, oh, you stick it there and it goes, that whole language goes away. But the language that persists is you have interactions. I mean, remember in physics 1 we say a force is an interaction between 2 things. That's why the force gets 2 indices. Here, that's the way we need to think, is that there's an interaction between fields. And Q determines the amount of that interaction. And of course, Q is an intrinsic property of the field psi. Okay, it's a thing we put in. Of course, we have to determine it from an experiment. But we're actually going to learn a very interesting thing about Q towards the end of the semester, and that is that it's actually not a constant. But more on that later.
Do you have to do anything different if you are dealing with like antimatter? Or does that?
No, you don't, because this is actually already describing antimatter. Remember the Dirac-Lagrangian and its extension to this local gauge invariance, all that includes the antimatter fields as part of the story. Now, you might be looking at it saying, doesn't antimatter have the different sign charge? And we're going to talk about charge conjugation a little bit down the road, and we'll see explicit. That's how we're actually explicitly going to be able to identify antimatter from matter is through this operation of charge conjugation, but I had to get charge in the story before I can talk about that. That's why I haven't really harped too much on it, but we'll get to that eventually, yes.
Is there a reason why you said that charge is a intrinsic property of the psi and not A? Is there a reason why? Because it appears in only in that term, Lagrangian.
So, the transformation that I was doing, okay, was defined in terms of this Q, and that was a global transformation before A was even part of the story. So if Q is associated with anything, it has to be associated with psi. Of course, from electromagnetism, we know that the electromagnetic field itself, A mu, is not charged. Okay? But even that is something which doesn't necessarily carry over to the other interactions. All right? So what I'm going to do now is, I'm not going to do anything new. I'm going to slightly rewrite some of this for two reasons. And I'm so glad David Schmidt left. Because in rewriting this, one of the things that we're going to do is we're going to see direct parallels with general relativity. For those of you who have taken GR, you're going to appreciate this. For those of you who haven't, one day you might, and you'll know, what you might anticipate. Okay? I'm not going to go into a lot of detail, don't worry. But the second reason I'm going to do this rewriting is because if we think about things in the right way, making the extension to the other symmetry groups that we'll talk about in the next two lectures will be more straightforward. Okay? It turns out that at least one step of what we did here was not quite the way we want to think about it when we move on to more non-trivial cases. Okay? So let me just do a slight rephrasing of this. And again, for those of you who have taken GR or know a bit about GR, you'll be very pleased to see some of the results that come out. So first of all, you might notice that in fixing our globally invariant Lagrangian to be locally invariant, the key was to change the derivative. Okay? Now, let's actually figure out what it was that we needed from our new derivative, okay, that allowed it to actually be locally invariant. So just focusing on the problem child, I don't need to work on the whole Lagrangian. The constants don't matter and the mass term is already invariant. When we transformed this term, we got this guy, and we couldn't pull the exponential across the derivative. And so that's why we couldn't make this simplification like that. Okay, so that's not equal. Okay, if we could have pulled this across the derivative, then we could have just yanked it out here, these two things would have canceled, and it would have been invariant. Okay? But here's the nice observation. This is going to look a little bit different than the way I wrote it before because I actually blew up the d mu, the capital D mu, into that. Okay? But here's the way the story works out if we actually work in terms of d mu. In this case, what we find, if we do the transformation, is that I've transformed psi with this term, but d itself transforms, because remember, d contains a, and a transforms. And what's nice, the useful property, is that this combination of transforming d and having this on the right becomes exactly moving this to the left. So in a sense, whereas our old derivative would not allow us to move this transformation across, in a sense, we can do that with the new derivative. But it's because the new derivative transforms. Yes?
And does that have to do with that whole product rule business where it pulled out each time and then you can factor it out?
Exactly.
Okay.
Exactly. So yeah, this looks a little. This is saying exactly what I wrote on the board before. It's just a little more compact because I'm saying it in terms of big D. So the derivative, the new derivative that we're dealing with transforms itself in a very convenient way, whereas the old derivative didn't. If you consider d mu and you ask, all right, suppose I have a bunch of functions of space-time, and they're written in terms of a set of coordinates, and then I decide I want to change coordinates with just some arbitrary coordinate transformation. So I'm doing something different now. This is what we just talked about. Now I'm talking about something different. What you would discover is that d mu, for example, d mu on a vector, does not transform in a nice way. In technical speak, what we would say is that this thing is not a tensor. You would like for it to be a tensor because it's got these indices, and you're like, it's a tensor, but it's not a tensor because it doesn't transform as a tensor under a coordinate transformation. But what we can do is we can replace this with a new derivative, which is the old derivative plus something called a Christoffel connection. And the benefit of doing that is that if I take the new derivative and I act on a vector, then this thing is tensorial. That is, when I transform it, I just get an overall transformation matrix acting on it. Now, there are a lot of details in there that many of you in the room are going, what? But for those who take a GR, they know exactly what I'm saying. Mark.
So when we did that, we called it the covariant derivative. Does the special derivative have a split?
Exactly. This is the covariant derivative of general relativity, and it is the way that you introduce gravitational interactions in general relativity. This is the gauge covariant derivative. They're all gauge covariant derivatives. The Christoffel connection in general relativity is the analog of the gauge field A mu. It was just some funny, weird thing. Remember, it's not even a tensor; it's a symbol. Right? Remember that it's a connection. We often also call it a Christoffel symbol. But you give it all of these indices. It's got like mu, nus, and alphas, but it's not a tensor. Okay, but that's okay because this is not a tensor either, and these two non-tensors combine to make something that's a tensor. But the point is, and for those of you who haven't taken GR, you should be going, ooh, I can't wait to learn that when I take Alex's GR class. GR, although it's a different kind of transformation, here I'm doing coordinate transformations, not some funny phase transformation. Here I'm doing coordinate transformations, but the story plays out very similarly. I need a new derivative because the old derivative didn't transform the way I wanted it to. But in forming the new derivative, I get interactions. Okay? Now, it gets better. Yeah.
So I feel like it's a bit of a strange use that the Christoffel connection is not a tensor, but IQ A mu is.
IQ A mu.
Or analog of the Christoffel connection in EM.
Why is IQ A mu a tensor?
Because A mu is a vector.
So you're talking about tensors under space-time transformations, which is what's relevant here.
Okay.
But here I'm talking about doing gauge transformations. So I should be asking, is A mu a tensor under a gauge transformation? And the answer is no, it's not. If I think of a tensor as something that transforms with this factor, that ain't how A transformed, right? A, where the hell did A go? Where does it say A? A transformed like this. It's not a tensor. But that's okay, because neither was D, but the combination gives you something that transforms with an overall factor of
The same thing.
e to the IQ 5. Yes?
So is it safe to say that when I'm trying to form a new, like this, like the Lagrangian is invariant under this type of transformation, that the term I have to add is not ever going to be invariant under it, that type of transformation, otherwise it would be useless? Because like in GR we introduced the Christoffel connection, which is not coordinate invariant, coordinate transformation invariant, and here we introduce a mu, which is not.
Well, right. I mean, if you started with something that was invariant and you added something that was invariant, you haven't fixed anything. Does that make sense? It's like if I start with a fraction and all I allow myself to do is add whole numbers to it, I'm never going to get a whole number out of that sum. I got to add a fraction. So I got to have two broken things combining to give me something that works. Okay. But that being said, the thing I add, the gauge kinetic term for whatever the new field is, that has to be invariant. Okay, so let me now talk about that, and we'll see another parallel to GR. Now, and this is a part of the story that is going to be very, very useful when we look at more complicated cases, because we would have missed this if we had just tried to naively take over the electromagnetism example. So, to get F mu nu, we just took the Proca-Lagrangian, which we've seen before, but there's a slightly different way to motivate what this thing should look like. And I'm going to work out for you right now what that is. What you can do is you can take your covariant derivative and form the commutator and let it act on a field psi. So if we do that, okay, I just write out what the covariant derivative it is, what it is. I'm going to go ahead and let the one on the right act on psi. And then I'm going to act on this with all of this stuff. If I see that, I kind of skipped over a little step that's in the notes. But now I just take this and I let each of these hit each of these, and in the end, I get a mess. And I can't even start to write. Holy shit. So I'm literally just multiplying that thing out. And wherever there's a derivative, I let it act on what it's got to act on. And there are product rules that are being used in this expansion. So you guys know how to do derivatives. Arms tired. Okay? And that looks exactly like what we thought. Because if I come in here, I notice I can commute partial derivatives. If I look at this, and I look at, what the hell is he? There he is. See that? If I look at that guy and that guy, they cancel. Holy crap. One of these should be new. I would have known that. Okay, those two cancel. And what I'm left with at the end of the day is IQ d mu a mu minus d mu a mu on psi. Which tells me that I could have just defined f mu nu as minus I over q times the commutator of the covariant derivative. Two points about this. Number one, this is the way you actually have to do it. The good thing is, though, this is guaranteed to give you something that's gauge invariant. What we'll find out is this original idea of saying this is d mu a nu minus d mu a mu, that actually won't be gauge invariant okay, under more complicated cases. But this is always guaranteed to give you something that's gauge invariant. And if you basically look at it, it's because these things transform the right way. So their product transforms the right way, okay? So we'll use this next time to talk about strong interaction. But the other thing that I'll point out is that if instead of thinking of internal gauge transformations, we actually asked about coordinate transformations, then we can ask, what does the commutator of covariant derivatives acting on a vector look like? And the answer is, that the commutator of the covariant derivative gives you what's called the Riemann curvature tensor of the space, which is exactly the field strength of the gravitational field in general relativity. And if you go back to your notes from general relativity, or if you want to read about this, this whole construction is the idea of taking a vector and moving it around a closed path and asking if it comes back to itself. This idea of parallel transporting around a closed path. And if you're on a curved space, you actually don't come back to the same orientation you started with. This calculates that for you, and the Riemann curvature tensor reflects the curvature of the space-time you're working in. So you can turn this story around and say that F mu nu is actually giving you a measure of the curvature of the electromagnetic field. And there's nothing wrong with saying this.
So now we could just plug in our new definition of F mu nu into the E&M Lagrangian to get
So this is the definition of F mu nu we're going to use. For E&M, it's the same thing as this. For the other interactions, this is going to give us some extra terms.
Okay.
But we need to use this because this is guaranteed to be gauge invariant. This, we just kind of got lucky that the Proca thing worked. Okay, we're going to have to work a little bit harder for the more complicated cases, and you'll see exactly why that's the case. And it's going to give us some new, the extra terms are going to give us interesting effects. Okay, so it's not just a complication, it's an interesting one. Guess what? I finished early.
Oh,
Yeah, Claire has it. I think, Claire, did you have a question? Or was it your hand being telegraphed back to Claire? Okay, go for it.
When you apply that to things that aren't electromagnetism, what happens to Q? Does that stay Q or?
So, interpreting what these things mean is going to be part. Next time we meet, I'm going to go through a very simple, a very similar calculation with some additional terms. But it's interpreting what we're doing that's going to be most of the lecture. Like, what does charge mean when you have three things versus one thing?
Right. I guess you just kind of came up with Q and then decided what it meant later.
Exactly.
I thought you said that's 5 minutes.
No.